Ma'am, you can start, ma'am.
Aparna ma'am, shall I start?
Yes, ma'am. Yes, ma'am. You can
Aparna
start,
ma'am,
ma'am.
shall I start?
Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am. You can start, ma'am.
Aparna ma'am, shall I start?
Ma'am, you can start, ma'am. Ma'am, we are live, ma'am. You can start, ma'am.
Okay. There is progress. Working together is success. Good morning and warm welcome everyone. It's our immense pleasure to have you all with us today for this webinar on an application in battery system organized by Faculty of Engineering and Technology, first year BTech, and Faculty of Education in collaboration with Office of International Relations. Evolving every second in the contemporary world, the need for energy contributing as the base for today's advancement, our webinar today is surely going to lead sessions ahead. We would like to invite Dr. N.S. Subhastri, Dean
Thank you, ma'am. Am I audible? A warm welcome to one and all present here. It gives me an immense pleasure in welcoming all of you to a webinar on energy storage devices. At this juncture, I would like to thank our beloved president and the management for permitting us for such programs even during the pandemic time. I extend my warm welcome on behalf of the organizers to our VC madam, who is always a guiding force for us, our registrar, additional registrar, joint registrar, sir, Dr. V. Srilraj, sir, are always a motivation factor. I also extend my welcome to all the other joint registrars, directors, deans, and other higher officials of our university for this webinar. It is indeed a pleasure to work with the Office of International Relations. And Dr. Kausalya madam has given us chance every time to work with them. So I happily extend my welcome to Dr. R. Kausalya and her team for this webinar. I also extend my welcome with gratitude to Dr. Geeta, Faculty of Education, Principal, Faculty of Education, and all her colleagues for this program, who is a co-host in this program. On behalf of our university, I extend my welcome to our chief guest of today, Mr. Mohd Faiz, who has given us concern to motivate us and to tell us about the hot happenings of the energy storage devices. Welcome, sir. Welcome to the program. I extend my warm welcome to all the teaching, the technical support staff, and all other staff members who have participated in this program. I also welcome all the participants, my dear students, for this webinar. So this webinar is going to be definitely very much useful, and it is going to open up many international collaborations. So once again, with deep gratitude to all those who have supported for this webinar to happen. Once again, I welcome all of you for this webinar. Thank you.
Thank you, Subhashri ma'am. Responsibility requires immense dedication and determination. Today, we have with us Dr. S. Geeta Lakshmi, Vice Chancellor, Dr. MGR Educational and Research Institute, a former Vice Chancellor of Tamil Nadu Government, the Dr. MGR Medical University Guindy, Director of Medical Education, Dean of Stanley Medical College, Madurai, Madras Medical College, Kilpak Medical College, and Director and Professor of Clinical Microbiology. The women of compassion and perseverance to support education through thick and thin of times. To S. Geeta Lakshmi to address the gathering.
Hello. Yes. Thank you for inviting me, and with great love for the education. Um, and I should thank our president, our chairman, and the head of the department, the registrar, joint registrar, who has been on the energy storage, energy saving, and I should also during this event uh, also request the head of the department, the students and the faculty to work upon it, not only our joint registrar and others who are working already working on it for years. I want all of you to get involved in it in different forms, and so today's discussion will throw a light on the energy saving mode and also the newer ventures for this energy saving. Unless we start practicing it ourselves, there is no use of telling or speaking or discussing on it. So I want you all to practice through our students and our faculty, so which would give them a light, throw them the light, and also to find out the various modes of energy like wind energy, light energy, where we use those energy for electricity and other sources of energy. So we would I also would like you to have a research on it, and I think so the head of the department is apt in doing it at a particular time during the COVID-19, and I also have come out from my COVID-19 pneumonia with a great benevolence from our God. And I thank you one and all for inviting me. Thank you.
Thank you, ma'am, for the inspiring and welcoming words. Success and achievements never come without appreciation. To felicitate the gathering with thought-provoking words, we are pleased to welcome Dr. V. Cyrilraj, Joint Registrar, Academics and Administration. Please, sir.
Good morning to all of you, respected Chancellor, respected President of our university, respected Vice Chancellor Madam for her inaugural address. Dear participants, I'd like to thank the resource person, Dr. Mohammed of MTU for his time. Dear students, the country like ours, a developing country, we are wasting around 3 billion unit of electricity produced. Most of the electricity we are generating through firing fossil fuel, at the cost of our Mother Earth. We are depriving the resources to our next generation also. And then we are making this earth non-livable also. There is another fact also. For generating 1 watt, 1 unit of energy, we spend around 150 liters of water also, pure water. So in all the way, no clear, we are polluting Mother Earth, but rather, so after generating this huge energy, we are wasting it. So that is a pathetic situation. So definitely, we need, we have to scale up the existing method of energy storages. Uh, all of us, we are aware of the rechargeable batteries. Clear. Right now, there are a lot of research are happening there in the rechargeable battery. So we think that that is only opportunities to store energy. But beyond that, no clear. There are a lot of scope available there. How we can store energy generated during the non-consuming hours, like during the nights, because actually we are not going to shut down our reactors or the hydroelectric plants or wind energy system, but rather we letting it wasted. So rather nuclear. So a lot of research are happening there to convert them as ice cube. Huge ice storage, or again using the excess energy to pump waters to the reservoir, and then again using those waters to generate hydroelectric energy during the peak hours, and then how to store thermal energy also. There are a lot of research which are happening there. How to store energy through the chemical reactions, and then there are a lot of research which are happening there to come out with the hydrogen cells also. So our world need a breakthrough in this particular, and then super capacitors. So like that, a lot of research are happening there. So dear students, if you have a basic knowledge on these technologies, so definitely your future is rest assured. When you take up your career, so definitely this will be a dominant career for another 30, 40 years. So till 2100, there will be a lot of opportunities in this particular domain, where the prediction says that the energy domain may have trillions and trillions of dollars of economic transactions also. So you could be one of a successful entrepreneur in this particular domain if you start right from today onwards, without wasting the time of our valuable resource person. I would like to thank the organizers, especially the Dean E&S, for choosing such a important topic for the discussion today. Thanks a lot for giving this opportunity.
Thank you, sir, for your words of wisdom. We would like to invite Mrs. L. Maria Suganti, Assistant Professor, Faculty of Education, to introduce the chief guest of the day.
Thank you, ma'am. I am profoundly delighted to take an opportunity to introduce our chief guest of today's session, Dr. Mohammed Faiz bin Hassan, lecturer, Advanced Nanomaterial Research Group, Ionic State Analysis Laboratory, Faculty of Science and Marine Environment, Universiti Malaysia, Terengganu. He has about 10 years of experience in the Department of Applied Physics, Material Science. His research interested areas are solid state materials, solid state ionic, composite materials, energy storage materials, conductive materials, functional materials, and metal matrix nanocomposites. He has published more than 30 papers in Scopus and Web of Science journals. He has a good reputation in his research profile and has secured 15 in H-Index. He has successfully completed 4 sponsored projects from various funding agencies and guided 4 MSc students in the field of applied physics. He has undergone more than 200 academic training and research activities. He has been resource person for various events. He has been the member of various professional bodies and NGO. He is a man with many feathers on his cap. He is a recipient of following awards: Outstanding Service Award in the year 2011, 2015, and 2018. Best Visual Aids Award in 2017. Achievement Award from 7 Earliest Training Days in the years 2014 and 2016. Anugera Malam Ilmu in the years 2011, 2012, and 2013. He has won bronze medal in Virtual Materials Technology Challenges 4.0 in 2020. He has won gold medal in Innovation and Research Week in 2021. It's a privilege to have such a renowned person amidst us. We are so happy to have you as a resource person through this virtual portal. Warm welcome to you, sir. Thank you.
Thank you, Mrs. Maria Suganti. Now we request Dr. Mohammed Faiz bin Hassan to enlighten our audience. Please, sir.
All right, thank you very much, the moderator today. Let me start with Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good morning for those in India time, and good afternoon for those in Malaysia times. Okay, first of all, I would like to thanks to respected VC and also the respected webinar committee of the MGR Educational and Research Institute of India for these invitations. I'm glad to be here, and yeah, that's to all the participants from India and Malaysia. I hope you all are doing well outside there. So very detailed introduction about me already given by our moderator just now. So no need for me to introduce again. It's good to start my talk now. So let me share my slide presentation right now. Okay, I share the screen. Okay, share with audio. This one. Okay, hopefully you can see the slide of my presentation right now. If don't, you can interrupt me and inform me. Okay, let's hit the button of slideshow. Okay, the title of the talk today is about energy storage materials, synthesis, characterization, and its application in battery system. Basically, my main field actually is material science. All right, so I will talking about the material, their synthesis way, how to obtain that one, and how to characterize. And when after finish the characterization, we try to employ them to be the what we call that one a useful component for especially for energy storage devices. Okay, basically I'm obtained my PhD from University of Wollongong, New South Wales, Australia in 2010. All right, already 10 years ago. And I'm one of the member of Advanced Nanomaterial Research Group, or known as ANoMa, under Faculty of Science and Marine Environment, Universiti Malaysia, Terengganu. All right, Terengganu is one of state of Malaysia. So back to the topic over here. All right. I will try to share something that I did during my PhD study until the current position as academician and researcher at Universiti Malaysia, Terengganu. All right, this is the outline of the talk today. Is divided into a few parts. Okay, it will begin with a brief introduction to the importance of our energy storage devices. All right, and it will follow by research for anode materials. Basically, this material will prepare it for lithium-ion battery. Okay, lithium-ion battery types, and these a few systems were selected. Basically, all this type of material is a carbon-coated material. The base is totally different. The first one is molybdenum oxide. nanobelt, and the second one, carbon coated material based on iron oxide nanoporous material, and the third one, the combination of two type of metal oxide, and we coat it with a carbon layer to be a nano composite materials. All right, and then the top we follow by a solid polymer electrolyte, okay, based on the starch doped or mixed with magnesium salt sulfates. All right, so and some acknowledgement will be our ending of this presentation. All right. Yeah, when talking about the energy storage materials, there are a few types of energy storage devices can be found outside there. For example, we have capacitor, supercapacitor, fuel cell, flow battery, superconducting magnetic, lantern heat storage, solar fuse, pump hydro, compressed air, and flyware. Yeah, I'm very interested with the some statement given by Dr. Khairul Raj about this field area. They have a very good and profit in future. All right. Okay. However, for this webinar, all the prepared material are specifically related to the battery as the most popular energy storage devices nowadays. Okay, so come to the question why energy storage are important. Yes, as we can see from the slide given here, the necessity of ESD stands for energy storage devices or battery as supporting energy devices extremely needed in a very big number or a huge amount to support the high demands, especially in consumer appliances, which using tablet, laptop, handphone, and other handheld devices. Okay, now this ESD is also required in what we call that one electric vehicle, all right, or hybrid electric vehicle to power up a hybrid or fully electric airplane, and in a large scale in megawatt hour, we can see that it can be as a backup power supply in especially in a smart city if you want to build that one. All right, it's also really neat in the renewable energy system. So without it, it will limit the application of the system itself. All right. So the usefulness of ESD can also be seen in many fields, as we can see from here, such as in mining, all right, spacecraft applications, all right, in military application, railways, and telecommunication system, and many more actually to be named. So I would like to share with you one of the popular example of the system that using a battery as the backup power system, which is a solar panel system. So basically, the system needs a battery to store the harvested energy from the sun, which can be used in a flexible way, all right, or time, especially at a remote area and or during the night times. All right, most of the closed system like this, okay, require the ESD or battery as a device to store the power element, and the system could be operated for longer times. So in material science, which I focus right now, where the study on the energy storage material is also hot, crucial, and as important as energy storage devices. All right. So let's gain some basic information about the component inside battery cell. So there is a battery diagrams. All right, it's containing three main parts of components or materials. So I divided based on ESM, energy storage material, conductive material, and non-conductive material. So we have the anode and cathode electrode here to be our ESM, energy storage material, and electrolyte and separator are the conductive material and non-conductive materials. So basically, this anode and cathode are two electrodes which provide the site inside the structure to store the ionic species of element which moves from anode or cathode to anode, depend to the charge or discharge reactions. All right. And for electrolyte, it's referred to the component which permit the ionic species moving through it. And whereas for separator, basically it's the component that block the anode and cathode from to be connected to each other. In other words, to prevent these two electrodes to get a short circuit inside the battery cell. This is the basic knowledge or information about the component inside the battery cell. Okay, so as I mentioned earlier, the study of anode material in this talk basically were conducted for lithium-ion battery types. So why lithium-ion battery? I think majority of us already know about the advantage of lithium-ion battery. Currently, majority of most of the appliances, electronic appliances using this type of battery in to power on them. All right. Okay, based on the given diagram here, we can see that lithium-ion battery become the battery type of choice in most advanced electrical appliances due to the high energy density, all right, of this technology compared to other type battery technologies such as in nickel type batteries and lead acid battery. So that's why we can get this type of battery in lightweight and very, very compact. All right. So it advantages like high cell voltage, cycle life, long cycle life, wide operating temperature range, and maintenance free, make it more superior compared to the other type battery technologies. All right. Again, this is the reaction mechanism of lithium-ion battery diagrams. So what I want to like here is the use of anodes and cathodes material in battery fabrication basically can determine the capacity of the battery itself. All right, for this webinar, I want to focus on this anodes material. Because the use of graphite or carbon in anode electrode nowadays already reach its limitations. So basically, what is the limitation of a carbon in this case of a lithium-ion battery? As we can see from here, the carbon actually has a limited specific capacity, which is about 372 milliampere hour per grams. And based on this value, it will restrict the lithium intercalation site inside the structure of anodes or cathodes materials. So by using this carbon, we also facing what we call that one low initial Coulombic efficiency, which is around 82 up to 88%. This is due to the irreversible capacity. After a few charge and discharge cycle, we cannot get this amount of capacity anymore. And by using this carbon as the anode material, so it will produce what we call that one poor electrolyte tolerance due to reaction with the electrolyte which are using the polycarbonate element inside it. Okay, in other words, the formation of SEI refer to the solid electrolyte interface layer present due to the reaction between carbon and also the electrolyte element inside that. All right. And to overcome such a problem, there are some potential candidates which can be used to replace the carbon as the anode material inside the lithium-ion batteries. So if you're familiar with this, what we call that one, a periodic table, okay, most of these elements basically are located in the middle of the table. So we refer to the metal oxide materials. So M here stand for, you can find out titanium, vanadium, magnesium, iron, cobalt, copper, stainless, silicon, molybdenum, and many more to be named, to be what we call that one substitute candidate for carbons. All right. So what is the advantages of metal oxides? So basically, as we studied in the previous time, we can see that this type of metal oxide actually have a very, very high lithium insertion capacity. Okay, most of the selected material which I studied before have around 2 or 3 times higher capacity than carbons. All right, by using this type of metal oxide, it also can produce what we call that one charge discharge in longer compared to the carbon element. And if we can produce this type of material, metal oxide, in nanoparticle size, we also can improve the cycle life of the battery itself. All right. So, however, from my previous study, I found only one obvious drawbacks on this metal oxide material, which is always facing or experiencing a poor capacity retention, which is referred to the phenomena where a large volume change on the material structure during lithium insertion and extractions. All right. So one of the potential energy strategy to minimize these drawbacks is by creating what we call that one a carbon layer on the metal oxide structural. Okay, why carbon coating? Okay, so this is an important question, why we need to use a carbon coating in this case. So we already mentioned that this is one of the strategy to reduce the volume change inside the metal oxide structure. Okay, yeah, this carbon coating actually has been studied by a few groups before. Okay, they prove that this is one of the effective techniques to improve the performance of electrode materials in lithium batteries. Okay, this carbon element also can act as what we call that one, an electronic conductor, and play a major role in supporting the conductivity of the cell. It also can act as a binding material, okay, to increase, okay, the contact between particles, thus prevent cracking and polarization. Polarization always occur during charge discharge, okay, where the particle from the big size becomes smaller size, and over there we can find that no connection in between particles themselves. All right. Okay, based on my previous study, most of the carbon obtained from this process actually tend to be highly amorphous and is provide the good mechanical properties, had a good very small particle size. However, I tried to find out their electrical conductivity, but I unsuccessfully to get it. However, we can yeah, basically this value actually taken from the published paper by someone else, right? So this is the TEM diagrams based on molybdenum oxide, which is coated with carbon. We can see that the beautiful carbon layer on the what we call that one structure of molybdenum oxide nanobelt with a good result which provide the good result in electrochemical performance. All right, let's enter to part one, which is about the carbon coated material which prepared for anode materials. As I mentioned earlier, that carbon coated based on molybdenum oxide, iron oxide, and the combination of two type of metal oxide, stainless oxide and nickel oxide. All right. Okay, this is the what we call that one experimental part, how to prepare the what we call that one a few type of metal oxide materials. I'm using two different types of techniques in order to get very good um, uh, nano composites and materials. Okay, in general, two different type of methods here refer to the hydrothermal method, and the second one is a molten salt method. Basically, for hydrothermal method, it was used to get molybdenum oxide nanobelt. To obtain this one, actually, we need to get our correct precursor first, add with some water, and then we need to add nitric acid to control the pH value inside the solution, and then this solution then put into hydrothermal reactor and then heat for 180 degrees Celsius for 30 hours. And after a few a simple process, we can obtain what we call that one molybdenum oxide nanobelt. Okay, the rest of the material actually I'm using molten salt techniques. So as we can see from here, to obtain tin oxide, carbon oxide nano composites, we need to start with 4 different type of precursor. So we need to make sure that the desired starting precursor need to be at the first stage, and then we need to mix together and drain until we get the homogeneous mixture, and then we add some hydrogen peroxide inside it until the preliminary reaction occurs, and then we need to heat at 300 degrees Celsius for 3 hours, and after a few a simple process after this, and then we can get what we call that one double metal oxide nano composites. This is the base material we obtain before we do some carbon coating on their structures. Okay, the prepared base material then will coated with a carbon element. The procedure is described in these diagrams. The first way, actually, the material are sonicated, need to be sonicated in toluene, and then we need to add inside the beaker, and this inside the beaker we need to add some amount of malic acid as our carbon sources, stir for 10 hours, and then the mixture was heated at 265 degrees Celsius to decompose this malic acid to the carbon elements. And after wash and heated at 100 degrees Celsius for 6 hours, we can get the material which coated with some carbon elements. All right, the as prepared material are tested in form of coin cell. All right, at the initial, the working electrode need to be prepared using the material as listed here. All right. For example, we already prepare for the active material, which is referred to the carbon coated metal oxide. We need around 88% of it, and we need to add some 15% of carbon black for the electrical conductor, and we also need to put some PVDF as a binder, and we actually dissolve these three type of powder in NMP to get what we call that one a slurry, and this slurry actually we need to paste on the current collector. Okay, so yeah, once we get the working electrodes, so we need to get another component like electrode based on lithium metal as the counter or reference electrodes. We need to using the spirator based on polypropylene with 25 millimeter thick and 50% of porosity. The electrolyte for this coin cell taken based on LiPF6 in 1 mole with in the solvent of EC/DMC 50/50 in weight. Okay, yeah, the arrangement of this all component basically refer to this beautiful diagrams. Over here we have a lead on the top and the lithium metal as the counter or reference electrode. We need to put at the first the second place, all right, and then followed by what we call that one spirator and electrolyte, and then we need to put our working electrode. Okay, in this case we need to put the anodes, and then we what we call that one close it with a can cover. So we need to use a special tool to close it in order to avoid the what we call that one the reaction from the outside occur inside the coin cell. Okay, this is some characterization technique which employed in the study, basically to identify the properties of prepared material that we synthesis in the early stage. Okay, we are using SRD in to determination of amorphous or crystalline of the structure for the prepared materials. Raman spectroscopy to detect some specific elements that cannot be detected by SRD. Okay, SEM basically refer to the microscope to take some useful image on the morphology of the prepared materials. And the last one is the battery analyzer. This battery analyzer actually is useful to get the electrochemical properties of the sample. All right, this is some what we call that one as the result for carbon coated and non-carbon coated materials. So as we can see from here, okay, based on the carbon coated patterns, so now no carbon peak can be identified by using the SRD analysis. Basically, the carbon is hard to trace in SRD analysis due to its highly amorphous, okay, and also due to the greatly crystalline structure of peak for the bare molybdenum oxide nanobelts. And in order to find out the carbon element on the carbon coated nanocomposite materials, we perform a Raman characterizations. Okay, we can see that based on this pattern, the carbon peak basically are located at these 2 points represented by these red arrows. Okay, the rest of the peak corresponding to molybdenum oxide. And in this characterization, we yeah, we're using the similar technique, which is our Raman spectroscopy to get the result based on carbon coated of iron oxide and stainless oxide, nickel oxide. And we confirm that, you know, the carbon layer and carbon element present in this all carbon coated compounds. All right, these are the TEM image for the carbon coated molybdenum oxide and iron oxides nanocomposite samples. To be highlighted here that the presence of a carbon layer, covering the main structure of molybdenum oxides and also in iron oxide structure. Okay. So similar results are also obtained for carbon-coated tin oxide, nickel oxide materials, as we can see from here that, you know, the particle of stainless nickel oxide, and we have another what we call that one a carbon metric, which covering this all nickel and tin oxide particles, and it is reasonable to conclude that the metal oxides in this case and also carbon particle are successfully intermixed. So this is one of the what we call that one electrochemical result based on carbon coated molybdenum oxide. As we can see from here that the red color is corresponding to the carbon coated molybdenum oxide curve. Okay, as can be summarized here, the carbon molybdenum oxide had the superior electrochemical activity in terms of capacity, as we can see from here. All right. Okay. Start from the first cycle. It has what we call that one, the capacity almost 1,400 milliampere hour per gram. And after 50 cycle, we can see that it still maintain in very good capacity at more than 1,000 milliampere hour per gram compared to without carbon coated. Okay, we have another similar result based on carbon coated of iron oxide. Okay, over here we can see at the specific capacity versus a cycle number graph, we can see that, you know, the cycle life of a capacity for the carbon coated material is superior compared to the bare iron oxide. Okay, similar result also obtained for what we call that one tin oxide, nickel oxides, nano composites. We can see that, you know, when we try to test this type of material with very high current density, as high as 800 milliampere hour per gram, we can see that, you know, this type of material still can maintain its capacity at almost 500 milliampere hour per grams compared to the sample without carbon coated. Okay, which stand at, you know, below than 100 milliampere hour per grams. So we can see that both nano composites, all the nano composites material based on carbon coated had the outstanding results in terms of capacity retentions compared to the sample without carbon. And we further analysis on the film of electrodes after cycling process. Cycling process actually refer to the charge discharge reaction that we test in our coin cell sample. And then we take some SEM images of the carbon coated materials. As we can see for this slide, we have images of carbon-coated molybdenum oxide before and after cycling. What can be seen here that the composite nanobed electrode had a tough film which sticks strongly to the substrate after a few cycles. By contrast, the bare nanobed electrode had a damaged films which contribute to the low electrochemical performance. We also get the similar finding for the carbon-coated iron oxide nanocomposite. So we can see that the big contribution from the carbon coating, which can prevent or reduce the volume change of composites during charge and discharge reactions. Not only that, it also can prevent cracking, and at the same time act as a conductive binder to increase the contact between particles, as the result preserve the excellent electrochemical performance to some extent. All right, as summary for this part, okay, a novel nanocomposite of molybdenum oxide, nanobelt, iron oxide, tin oxide, nickel oxide powder coated with conducting carbon was successfully prepared by using a simple carbon coating method. The second one, the carbon coated anodes material have higher capacity and improve the cyclability compared to the bare molybdenum oxide anodes. All right, next, carbon matrix is suitable to increase the electrical conductivity and prevent cracking and grinding of the molybdenum electrodes. In general, this carbon is well known as a conducting substance, and in matrix form of carbon, you can see that MO metal oxide particle can be bound together. The particle-to-particle resistance will be decreased. And this carbon also managed to buffer the volume change of the metal oxide during charge-discharge cycle. And next, this carbon also can act as a host matrix to prevent cracking and crushing of metal oxide electrodes. So as the result, the carbon-coated nanocomposite material provide the outstanding electrochemical properties in rechargeable lithium cell as shown in previous slides. All right, so let's enter to part 2, which is about the polymer electrolyte. Yeah, based on starch and manganese sulfates. Okay, let's understand about the terms of polymer electrolyte first. Basically, it is referring to as a medium which has an ionic conductor or a medium for transfer of charge. Okay, ion is inside the cell between anode and cathode. All right. Ionically conductive, but is also electronically insulating. Okay, which preventing a short circuit circuiting occurrence inside the cell. Okay. So the term of polymer electrolyte is referring to liquid or solvent-free material. Salt and solvent are dissolved or mixed with high molecular weight polymer. Okay, so the role of the polymer electrolyte basically to be as what we call that one ionic carrier. It also can be as what we call that one electrode spacer. Okay, and the last one also can be as what we call that one binder to ensure a good electrical contact between the electrode surface in the battery systems. Okay, the polymer electrolyte can be produced in 3 forms or 3 types. We can get it in liquid form, gel, and also solid. Okay, in this particular discussion, I will discuss on the solid polymer electrolyte. Okay. Yes, there are no doubt that solid polymer electrolyte have some advantages as listed here. It has no possibility of leak. It also can strengthen of cell, okay, thanks to all solid state construction. Its shape flexibility can be manipulated in easy way. All right, it also can lowering the cell weight. Or solid state do not need heavy metal casing during battery fabrications. Okay, some dendrites that grows during discharge process can be prevented if we're using this type of electrolyte. Okay, it also has what we call that one better overheating and wider operating temperature, which is from negative 40 degrees Celsius to 150 degrees Celsius compared to the liquid electrolyte in the range of negative 15 degrees Celsius to 60 degrees Celsius. So the last one, it also can, what we call that one, can improve the safety of the cell itself. So to prepare a solid polymer electrolyte, the selection of starting material are also crucial and important. So for this case, starch is chosen based on two main factors, which first is renewable and biodegradable plastic and has a very good flexibility properties. And the second one, based on previous work done by some researcher, they prove that uh, um, its bare ionic conductivity can be boosted after mixed with some potential ionic booster or salts. Okay, and for the ionic booster, okay, magnesium sulfate is selected based on previous work done by a few groups. They prove that it's always used. Uh, they always use this magnesium sulfate as the ionic booster in solid state fuel cell, supercapacitor, and battery. Okay, some other researcher also mix this type of salt with other type of polymer, and they got the outstanding ionic conductivity. So based on the information on that time, there was no information the complexation between starch and magnesium sulfate done by people outside there. So that's one of the what we call that one effort be done to create a new type of system for solid polymer electrolyte. Okay, basically this is one of another information for the starch. Yeah, I'm not touch it this time. So just to refer to this table. All right, this is the table of the list of positive and negative ion. Basically, there are many ionic species can be selected depend on the study purpose. So far, most of my study focus on the positive ion as the what we call that one to move from anode to cathode to anode. So in this case, I choose sodium plus and magnesium plus. All right, this is due to the the system quite close to the lithium ion battery systems. Okay, in this preparation sections, the film is prepared using what we call that one a solution casting techniques. Okay, starch and magnesium as our starting materials. Okay, firstly, starch powder is diluted into the prepared solution. We using water and what we call that one glycerin as the solvents. Okay, subsequently, different amount of magnesium salts are added into the solutions, and after obtained a homogeneous mixture, then pour into what we call that one petri dish and left for naturally dry. Okay, after a few days, a mechanically strong, transparent, and freestanding film is obtained. So in order to test the functionality of our solid polymer electrolyte, we need to fabricate batteries. Okay, so most of the material to fabricate the battery taken from the market. Okay, and the arrangement of the component over here basically refer to this diagram given in the slides. Okay, and this is the real type of battery that we develop in our lab. All right, we also test our battery cell using a simple electronic circuit as shown here. All right, we built this circuit in our laboratory by using a few electronics components, namely a step-up transformer, 2 kilo ohms resistor, BC transistor, and also one LED. All right, this is the structure modification and evolution of the morphology and the electrical property basically were investigated by these selected techniques. All right. There is some result that we obtain from the film that we produce in our lab. Okay, as we can see from here that the film with transparent color based on this complexation can only be formed at the certain amount of ionic salt. Okay, and from the SRD pattern here we can see that the film has a definite lightness and present in a greatly amorphous phase. Okay, the result also revealed that the coexistence of peak of the investigated material rectify their complexation in solid polymer electrolyte films. So we have another what we call that one FTIR spectra result here. Okay, we identified this all peak actually corresponding to the starch. Okay, we found that no peak can be correspond to the magnesium sulfate. However, we found that when we add the magnesium sulfate, we found that some peak shifted to another positions, and based on the discussion given by the some author, they said that this shifting occur can be confirmed the chain reaction or addition from reaction process successfully achieved in the systems. So we have the SEM image of the film. Okay, the film have some agglomeration surface with a circle shape, then became flat, joined each others, and some pore structure obviously appear in the specific area of the samples. So we also calculate the pore size was estimated to be in a diameter of 20 to 70 nanometer, and thought to be this interesting property actually have their own contribution to enhancing the electrical property of the films. Okay, this is the result of the electrochemical testing of the battery that we developed in our labs. Okay, so we can see that the first upper small graph illustrate the open circuit voltage of fabricated cell. At the first point of the measurement, the voltage cell was 1.5 volts and dropped to 1.43 volt for 14 days, which equivalent to 4.7% reductions. So based on this preliminary discharge profile, we can determine that the cell has the capability to supply the current up to 50 microampere for 65 minutes, and it is a reasonable result obtained for the small size of the constructed cell in this work. Okay, this figures demonstrate the electronic circuit which are connected to the as fabricated zinc carbon cell that we developed in our lab using the as prepared solid polymer electrolyte. We can see the completed circuit is with no connection over here on the negative terminal of the cell. Okay, from this circuit, we can see that LED in this small image was not lighting on. Okay, when we connect the negative terminal of the circuit to the negative terminal of the cell, we can see that, you know, this complete circuit permits the LED light up, as we can see on the small picture over here. Okay, so to be noted here that the as fabricated cell has been prepared for almost 6 months ago, and incredibly it still can supply the power to the circuit. So this initial result revealed that the as prepared solid polymer electrolyte has a good performance not only in zinc carbon battery but might also in other type of electrochemical devices. Okay, as the summary for this part, a novel solid polymer electrolyte based on starch complex with ammonium sulfate have been well prepared by a simple solution casting technique. Okay, the complex film was highly in amorphous rather than the crystalline phase with conductivity of order of 10 power of negative 5 cm per centimeter at room temperatures. And solid state zinc carbon cell using the prepared polymer electrolyte has been successfully assembled and examined. The preliminary result on the electrochemical performance of the cell demonstrate that the as prepared solid polymer electrolyte can be employed in battery system and maybe in other related devices. Okay, all the research work shared here basically been published in this article. All right, start from 2011 until now. Okay, this is the latest of publication that we obtained in 2021, where we prepare the system using the starch doped with sodium bisulfate, which published in basically in Malaysia journal. All right, so for the acknowledgements, I would like to take this opportunity to thanks to UMT and Malaysia government for the funding of this work, and to thanks also to FSSM and FTTKI for the facility support, and also to my research collaborator, the list here, and not forget also to the partner over here from Dr. MGR Educational and Research Institute of India. Thanks a lot for giving this opportunity to be here. I pray for Malaysia and India in fighting the COVID-19. So that's all. Thank you very much for your attention.
The possibilities are endless when you have the tools you need to learn. Thank you, sir. Your presentation captured the attention of all. The session was really useful and informative. Thank you, sir. Knowledge is gained by asking questions and seeking answer. We request the participant to ask questions to which our guests would answer. Sir, we have few questions from Prithvi Pratap. The first question is, how does the alkalinity or acidity affect the morphology of the biochar particles for energy storage applications?
Yeah, basically to answer this question, I think you refer to the what we call that one, the preparation of molybdenum oxide by using what we call that one, hydrothermal method, right? Over there, we need to control the pH solution inside the solvent. Basically, if we do some detailed experiment on that particular technique, we can find that, when we control the alkaline and also acidity of the solution, we can change the morphology of the structure. However, for this case, I'm not deeply involved uh, uh, to play around with acidity and also alkaline to get the what we call that one to play around with the morphology of the material. The formula taken from directly from the published paper. All right, we just follow 100% the formula given over there in order to know the what we call that one the material that we want to get it at the end of the process. Did I answer your question?
Okay, sir. I'll ask the second one. What are the difference between coin cell batteries and coin cell supercapacitors?
Okay, what the difference between coin cell battery and coin cell capacitor? Basically, for capacitor, the electrode using inside there both are the same material. But for battery, we need to get the electrode with different type of material. Okay, so that's my answer.
Okay, sir. I'll move on to the next question. Why open circuit potential of half-coin cell changed before and after formation cycles?
Yeah, basically, if you study about the electrochemical inside the battery, you will know that, when you test without load, you can see that at the beginning of the voltage, it start, for example, 1.5 volt, it will, change by time. This is due to the internal resistance inside the coin cell. Okay, if the internal resistance is bigger, you can see that the open circuit inside there will reduce in high percentage. Okay, so that's why the internal resistance inside the cell is quite important to take note. We need to make sure that the internal resistance inside it as low, as small as possible.
Thank you, sir. I'll move on to the next question. Is it possible to open the vent in lithium-ion battery using the short circuit?
Basically, for lithium-ion battery, you need a special environment. In my case, I'm fabricate this type of battery in what we call that one glove box. The environment inside the glove box actually is argon gas, so you actually can open without the special tool in order to what we call that one to characterize or to do some simple experiments.
Okay, sir. How to select anode and cathode size? I studied that if we keep them equal and if there occurs slight mismatch, it will be a problem. What is the answer for this, sir?
Ionosparator should be largest. Ionosparator should be largest. How to select anode and cathode size? I studied that if we keep them equal and if there occurs slight mismatch, it will be problem. Lithium plating or less capacity. Yeah, basically to answer this question, can you open again the question? All right. Yeah, exactly. The sparator should be larger than the size of anode and cathodes. If the similar size, you will found that the cell will be in short circuit. So that means it cannot be a battery anymore. All right. So basically, to find out that capacity for this type of battery, we need to do some not simple calculation by using their theoretical specific capacity. From there, you can find out that uh, how to get the correct capacity of the battery.
Okay, sir. The other question is how to avoid slump formation while making slurry for lithium-ion battery cathode material.
Okay, how to avoid lump formation while making slurry for lithium-ion battery cathode material. Yeah, basically there are many technique and many method in order to avoid lump formation during slurry formation. That's a technical what we call that one. Yeah, actually that one is a technical way how to do that one. Basically, in my case, I using what we call that one methanol to make the celery, and we add that methanol inside the material that we add in the what we call that mixer, and then from there we stir for a few hours, and after that we pour that celery on the what we call that one on the glasses, and after that we left it dry naturally, and that the methanol easily to be evaporate. Okay, so from there you can see that no lump formation can be found from the cathode material. Okay, that one of the what we call that one way how to avoid the lump formation on this celery film.
Okay, sir. Thank you, sir. One more question. Can producing hydrogen from DI water in strongly acidic or alkaline conditions truly lead to sustainable solution to the future of energy storage? Please, sir.
Basically, I have no knowledge about this hydrogen field. Yeah, how to answer that one? I have no answer for this question.
Okay, sir. Okay, then I'll move on to the other one. How nanotechnology material improve the cycle life of metal oxides?
Okay, how nanotechnology can improve the cycle life of material? Yeah, basically you can see that the small size of the particle, you can get what we call that one more particle which can involve the reaction with the positive species of that move from anode to cathode. And the second one, when you have the nanoparticle size, you can see that the distance between these two particles become less, and it only take a short time to reach to one position to another position. That means they need only a small energy to complete the reactions.
I think that's all, sir. That's all, sir. Thank
Right.
you, sir. Thank you. Thank you,
Okay.
participants, for the enthusiastic participation. A feast is never complete without a dessert. So is an event never complete without a proper thank note. We welcome Dr. K. Geeta, Principal, Faculty of Education, to propose vote of thanks.
Good afternoon to everyone. Thank you for this opportunity to thank everyone. First, we thank the Almighty for the grand success of this international webinar. Our hearty thanks and gratitude to our Honorable Chairman A.C. Shanmugam and Honorable President A.C.S. Arun Kumar of Dr. M.G.R. Educational and Research Institute to permitting us to conduct such a useful international webinar. Our sincere thanks to today's speaker. It was very interesting live session. Dr. Mohd Faiz bin Hassan, Lecturer, Advanced Nanomaterials Research Group, University of Malaysia, Terengganu, for your informative and interesting speech. A very good presentation we had today by stating the importance of energy storage devices, components in a battery cell, and then molten salt techniques, carbon coating, and discussion about XRD, XD, TEM discussion part after cycling process of SEM and polymer electrolyte, like that, so on. So many information you are given for all our students. It was very interesting, sir. So on behalf of everyone, my hearty thanks for you. Also, I thank Dr. On Jain, Malaysia, for introducing such a wonderful speaker to make today's session very interesting and very informative. And I would like to thank our Vice Chancellor, Dr. Geeta Lakshmi Madam, for her valuable inaugural address. Thank you very much, Madam. And we thank Dr. Cyril Raj, Joint Registrar, Academic, for his keynote address. Thanks a lot, sir, for your keynote address. And we thank Dr. Subhashri Madam, Dean, and Kaushalya Madam for this collaborative work to support our department and to include us uh, to this international webinar. We are proud to be a part of this. This is because of Dean Subhashri Madam and Kausalya Madam. Thanks a lot for both of you, Madam. And our thanks to all the executives of our university for their encouragement and support. And thanks a lot for our registrar, always he will support us. And thank you very much to all the participants. Our heartfelt thanks to all the participants from our university, as well as from various university, students, faculty members, and other academicians for your interesting participation and interaction with the question and answer session. So once again, thanks to all the participants. Thank you very much for the teaching and non-teaching faculties and technical support given by the faculty members to conduct this webinar a wonderful success. Thanks to one and all. Thank you very much to all of you. Thank you. Thanks a lot, sir. Faiz, sir. It's a very nice session we had today with you.
My
Thank
pleasure.
you very much.
Right.
The aim of education is knowledge, but action. Let us act with the knowledge gained. Thank you all for making the event engaging and amazing. Thank you.